13 billion light-years away, in the frozen dark, something impossible is staring back at us. A smear of ancient light so faint it should have been lost to time has reached a mirror hanging far beyond the moon. That mirror belongs to the James Webb Space Telescope, and the message it carries is simple and unsettling. The early universe was busier, brighter, and stranger than we imagined. Welcome to a calm journey through that discovery. We will move slowly, speak plainly, and let the night sky unfold without hurry. No dense equations, no tangled jargon, just clear ideas you can follow with your eyes closed. If that sounds good, take a gentle moment to like this video and subscribe. It tells the algorithm to send more people a soft, science-rich story to drift off to and to wake up curious. Here is the promise. Webb has looked deeper into the past than any telescope before it. In the glow of its deepest images, we see young galaxies that already look mature, compact, bright, and busy, at a time when the universe should have barely learned to make stars. We also find hints of giant black holes appearing early, like engines that somehow started before the car was built. And as a bonus, Webb can read whispers from faraway planets, tracing the thin chemistry of their skies. For decades, our picture of the first billion years after the Big Bang seemed tidy. Space was hot, then cooled. A fog of neutral gas trapped light. When the first stars ignited, their energy burned away that fog, and small, messy galaxies began to form. Big, orderly galaxies were supposed to take their time. Webb's view complicates that story. In fields of almost empty darkness, it finds islands of starlight already organized, as if the universe pressed the fast-forward button. How could that happen? One idea is that stars formed with unusual speed back then, turning cold gas into light with a kind of cosmic efficiency we rarely see nearby. Another is that there are simply more early galaxies than we expected, and we are finally sensitive enough to notice the bright ones. A third possibility is that our methods for translating faint light into distance and mass need careful tune-ups at the extremes. None of this breaks physics. It strengthens it by forcing better questions. Now the black holes. In our cosmic neighborhood, almost every large galaxy hosts a massive black hole at its center. These engines feed on gas and dust, sometimes lighting up the galaxy with fierce outbursts. Webb's deep stare suggests that some of these engines were already heavy when the universe was still young. To grow so quickly, they may have been born big, from the direct collapse of enormous gas clouds, or they learned to feed with startling efficiency. Either way, their early presence changes the timeline for how galaxies grow. Webb's power does not stop with galaxies. Its instruments are tuned to infrared light, the glow of warm dust, and the stretched-out light of very distant objects. When a planet outside our solar system passes in front of its star, a thin slice of starlight filters through the planet's air before reaching us. Molecules like water vapor, methane, and carbon dioxide leave tiny signatures in that light. Even across impossible distances, we can read those signatures like a barcode. That turns distant worlds from points of light into places with weather and chemistry. What then is truly shocking? The shock is rhythm, not rule-breaking. Gravity still pulls, and light still travels. But the universe uses those rules with more urgency than we expected. Where we pictured a slow, careful climb from simple to complex, Webb shows a sprint. Stars forming fast, structures assembling early, black holes arriving ahead of schedule, and planets offering measurable hints of their skies. If you are new to telescopes, imagine Webb as a time machine made of precision and cold. Its gold-plated mirror is larger than a house and shaped like a honeycomb. It unfolds in space and focuses on light so faint it would be invisible to any human eye. The whole observatory is kept colder than ice, so its own warmth does not drown out the signal. Because the universe is expanding, the oldest light has been stretched into infrared colors, the exact range Webb was built to see. That is how it looks so far beyond what we once thought possible. Here is how we will travel together. I will keep the language clear and the pace gentle. For distance, we will start with steps, roads, and Earth to Moon, and only then reach for light years. For size, we will compare to cities and continents before talking about galaxies. For time, we will speak in lifetimes and generations first, then in the deep ages of stars. The goal is simple: turn the night sky from an abstract picture into a place you can visit in your mind. Across this series, we will follow 3 threads. First, the 2 early galaxies, how Webb found them, what their light reveals, and how the first star factories might have raced into action. Second, the grown-up black holes in a baby universe, possible origins, growth spurts, and how their hunger shapes everything around them. Third, the planets and rogue worlds, how we read their thin airs, what chemistry we have glimpsed, and where the search for life may realistically lead. For now, take a breath and look up, if not with your eyes, then with your imagination. The sky above you is the same sky that fed Webb's mirror with ancient light. Somewhere out there, young galaxies are blazing, black holes are waking, and lonely worlds are drifting like embers. They are not waiting for us, but they are willing to be seen. And for the first time, we have the tools to see them clearly. Settle in. The universe is ready to tell a different version of its origin story. And you are here for the first chapter. Imagine holding a mirror so perfect that it can catch the faintest glow from a candle a continent away. Now move that mirror beyond the moon, unfold it like a golden flower, and keep it colder than the winter night on Antarctica. That is the essence of the James Webb Space Telescope. It lives at a quiet parking spot in space called L2, where the pull of the sun and Earth balance just right. There, it floats in a steady shadow, protected by a 5-layer sunshield as large as a tennis court. Those layers act like umbrellas inside umbrellas, each one reflecting heat away so the instruments can stay cold and calm. Cold is not a luxury. It is the only way to see the oldest light, which has been stretched into infrared by the expansion of the universe. Think of light like a note in music. When a source moves away, the note slides lower. In space, as galaxies drift with the cosmic expansion, their light slides to longer, redder wavelengths. Over billions of years, that slide turns visible starlight into infrared glow. To human eyes, it is invisible. To Webb, it is a clear voice. This is why Webb looks like a time machine. The deeper it stares, the further back the light comes from, and the younger the universe appears in its images. The mirror itself is a honeycomb of 18 hexagons, each coated with a whisper-thin layer of gold. Gold is excellent at reflecting infrared. The segments can tilt and adjust by tiny amounts, smaller than the width of a human hair, until they act as one flawless surface. When the observatory first unfolded, engineers nudged each piece again and again until the starlight focused to a pin. Once aligned, the mirror feeds that light to instruments that split it into colors with extreme care. Those colors carry the story: how fast a galaxy is moving, how old its stars might be, what elements live in its gas, even whether dust is hiding newborn suns. For years, astronomers planned deep surveys with names that sound like invitations: early release science, CERs, JADES, glass. Each was designed to push a little further, to test how quickly structure appeared after the Big Bang. Before Webb, the standard picture said the first galaxies were small and chaotic, like tiny towns forming before cities. The surprise in those early Webb images was not a single oddball. It was a pattern. Over and over, the telescope found compact, bright islands of stars already shining with confidence. They looked like cities with lights on, at a time when the power grid was supposed to be barely built. Why does that matter? Because the timeline shapes everything else. If stars formed faster, they poured energy into the surrounding fog of hydrogen sooner, clearing it away and letting light travel freely. That process, reionization, is like the universe turning from mist to morning. If black holes formed early, they could have steered the growth of their host galaxies, stirring and heating the gas, deciding where new stars could be born. And if our methods of estimating distance from color need fine-tuning at the edge of what is measurable, that tells us to be humble and careful as we decode faint signals. None of this means the laws of physics are broken. It means the universe used those laws with urgency. Gravity gathered gas. Gas cooled and collapsed into stars. Stars lived, died, and seeded space with heavier elements. But the pace may have been livelier than our first drafts guessed. Imagine arriving at a town you thought would be a camp and finding paved streets, market stalls, and a clock tower. The rules of construction are the same. The schedule was simply tighter. Understanding that schedule depends on spectra, the rainbow fingerprints hidden in the light. When Webb spreads a galaxy's glow into its thin bands, tiny lines shift to the red by a measurable amount. That shift tells us how far the light has traveled. It also reveals chemistry. Hydrogen, helium, and traces of heavier elements leave distinct marks. Young galaxies with very few heavy elements look different from later ones, seasoned by many generations of stars. In this way, Webb does more than take pictures. It does forensics, pulling clues from whispers. The same tools work for planets. even when those planets are only dots we never resolve. When a world passes in front of its star, a sliver of starlight filters through the planet's atmosphere. Molecules in that thin air absorb certain colors, leaving notches in the spectrum. Water vapor makes one pattern, methane makes another, carbon dioxide leaves its own trace. By comparing the star's light during and after the transit, Webb can read those notches and sketch a profile of the planet's sky. It is like tasting a soup by the hint of steam coming off the bowl. You do not see the vegetables, but you know they are there. Keeping the observatory cold and stable is what makes all of this possible. The sunshield blocks the raw heat of the sun, Earth, and Moon. Radiators bleed away the telescope's own warmth. One instrument carries a tiny refrigerator that reaches temperatures near absolute zero. At those depths, the detector's electronic snow settles down, and the faint cosmic signal rises above the noise. In such silence, a distant galaxy that would be invisible to Hubble becomes a steady glow on Webb's sensors. There is a quiet confidence in the way this system works. No frantic chasing, no whirling mechanics, just patience and precision. The telescope points, holds, and drinks in light for hours. Later, on the ground, teams clean the data of cosmic rays and stray reflections. They align exposures, stack them, and let the faint build into the real. Only then does the scene emerge. Beads of galaxies on invisible threads, dusty nurseries where stars ignite, and here and there, the compact hearts that hint at early black holes. When you hear that Webb found galaxies too big, too soon, treat it as an invitation, not a verdict. It invites us to ask better questions. Did star formation run hotter in the first ages? Are we preferentially catching the brightest examples, the flashy tip of a much larger population? Do bursts of starbirth make galaxies look heavier than they are, tricking our estimates? Each possibility can be tested with more spectra, longer exposures, and cross-checks with other observatories. Science grows not by avoiding surprise, but by folding surprise into understanding. The night is wide. Our pace here will stay gentle. We will keep building from the simple to the deep, so the story can carry you whether you are fully awake or drifting toward sleep. What matters is that the light is honest, and our curiosity is patient. The universe is speaking softly in infrared, and for the first time we have an ear tuned to its oldest songs. Picture the newborn universe as a dim, foggy shoreline at dawn. The first campfires are trying to burn through it. Those campfires are the earliest stars. Their light is harsh and blue. When enough of them flicker on, the fog, the free hydrogen gas between galaxies, begins to thin. Astronomers call this clearing reionization. It is a slow sunrise spreading across space. Webb can see both the fog and the fire, catching the moment the night gives way. Here is a simple way to think about it. Early space is full of raw material, like a warehouse stuffed with boxes of gas. Gravity is the forklift. It lifts the heaviest stacks first, and the boxes slide together. When they compress enough, a star sparks. Groups of stars gather into small, lumpy galaxies, and those merge to make larger ones. We used to think the warehouse rules were strict and slow. Webb shows the forklifts were busy. Many stacks collapsed early. Many neighborhoods lit up sooner than expected. You might ask, if the universe is so young in these scenes, where do the heavy elements come from? The carbon in our bodies, the oxygen we breathe, the iron in our blood. Those do not appear at the beginning. The first stars are mostly hydrogen and helium. They live fast, die in explosions, and in those deaths forge the heavier elements. Think of them as cosmic kitchens. Webb's spectra can tell when a galaxy has already cooked a little or is still mostly raw ingredients. That in turn tells us how many generations of stars have come and gone. Now to the engines at the centers, black holes. The phrase sounds like a trap, but a black hole is better pictured as a drain where space itself is flowing inward. Most big galaxies host one. The puzzle is how some of these drains became large so quickly. There are two main ideas. One is that the first giant stars collapsed and left heavy seeds, which then ate greedily. The other is that, in rare places, huge clouds of gas fell straight in before they could split into many stars. Webb cannot watch the birth directly, but it can weigh the surroundings and see the signs of a young engine feeding early. Webb also listens for smaller, quieter stories, the weather on planets. When a hot, puffy world swings across the face of its star, a thin ring of starlight passes through the planet's air. Molecules leave tiny signatures: water vapor, methane, carbon dioxide. Each snips out very specific colors. Webb has read some of these barcodes from faraway giants. They are not Earth-like, and that is fine. Learning to read easy targets now teaches us how to read trickier ones later. It is like practicing on bold headlines before attempting fine print. Signals sometimes come from loners, two rogue planets, drifters not tied to any star. They are hard to find, but Webb can feel their warmth if they cross background starlight or if they glow in certain bands. The idea that there are worlds wandering in the dark, cooling for billions of years, gives the galaxy a restless mood. Not every story needs a Sunday. One useful habit in this field is caution. A bright, compact galaxy can masquerade as a heavyweight when a short, furious burst of starburst is doing most of the shining. Dust can hide parts of a system and shift colors in ways that confuse distance estimates. Even a chance foreground galaxy can act as a magnifying lens, bending and boosting the light of one behind it. Webb's sharp vision helps sort these tricks, and pairing its data with other observatories keeps us honest. Why does any of this matter to a person lying in bed, phone on the nightstand, eyelids heavy? Because this is the story of how structure forms, and you are made of structure. The calcium in your teeth was baked in ancient stars. The oxygen in your lungs was blasted into space by a supernova. The iron in your blood was hammered in the core of a dying giant. When we say Webb is looking at early galaxies, we are also saying it is looking at steps that led to you. Knowing when the first cities of stars turned on helps explain why the universe looks the way it does now. Let's put scales in reach. If the Milky Way were the size of North America, our solar system would be smaller than a pinprick on a city map, and the Earth would be a mote inside that pinprick. The light reaching us has been traveling not just since before you were born, but since before the Earth itself formed. Receiving it now is like hearing the echo of a match struck in a distant canyon and only now reaching your ear. There is a courage to this work. Teams plan for years, argue over details, send an observatory to a point 1,000,000 miles away, and then wait. The first data arrive as faint numbers. They clean it, compare it, and ask if a surprising result is a new truth or an old mistake in disguise. When a result survives every test, it earns its place. That is how science keeps its balance open to wonder, anchored by checking. As we continue, we will visit specific deep fields and the strategies behind them, how astronomers aim at patches of sky that look empty and build a portrait of the early cosmos, dot by dot. We will listen for the thin notes of different elements in a spectrum and translate them into age and distance in plain language. And we will keep returning to the big question: did the universe truly build early and fast? Or are we finally seeing a crowd that was always there, just beyond our reach? For now, relax your shoulders and drift with that shoreline at dawn. More campfires are catching. The mist is lifting. And just beyond the brightening edge, the first cities of stars are about to wake. Start with a picture in your mind. A deep field from Webb where the background is not empty at all, but crowded like a night beach lit only by fireflies. Each spark is a galaxy. Some are big and smooth, like slowly turning wheels. Others are small and sharp, like fresh sparks just thrown from the fire. Here and there you notice stretched arcs, as if someone took a paintbrush and pulled the light sideways. Those arcs are the first clue that gravity can act like glass. This effect has a quiet name: gravitational lensing. A heavy cluster of galaxies sits between us and the deeper universe. Its gravity bends space slightly, the way heat shimmers bend the view above a road on a hot day. Light coming from behind the cluster travels along curved paths, so background galaxies look larger, brighter, and sometimes copied into multiple arcs. To a sleepy eye, they are pretty curves. To astronomers, they are magnifying glasses gifted by nature. Webb pairs its sharp vision with these cosmic lenses to peek even further back than its mirror alone would allow. Follow one of those arcs. The color leans to red because the universe has stretched the light during its long trip. Webb can turn that warm color into a number: how far, how old, by splitting it into a spectrum and reading the tiny shifts in known patterns. When the shift is large, we are seeing a galaxy that shone when the universe was still young. What startled researchers in the first surveys was how many such candidates appeared in one field after another. Not one odd ancient spark, but a handful. Not a handful, but dozens as the exposures stacked up. Now let's walk gently through how a deep survey works without drowning in jargon. Teams pick a small patch of sky and return to it again and again. Each visit adds more exposure time, like letting a camera keep its shutter open a little longer each night. Faint things rise out of the noise. The first pass spots likely galaxies based on color. The second and third passes aim for spectra, those thin rainbows that let you check distance, chemistry, and whether dust is hiding newborn stars. Over months, the portrait sharpens. You go from "there is something there" to "there is a compact, star-forming galaxy there with little dust and not much heavy element seasoning." That is the moment the early universe stops being a rumor and becomes a map. Why the focus on compact and bright? Because those words hint at intensity. A compact galaxy can pack its gas tightly, feeding star formation at a high rate. Brightness tells you that many young, massive stars are burning at once, or that a central black hole is adding its own light as it feeds. In the nearby universe, we call such events starbursts and active nuclei. Seeing them this early suggests the first cities of stars did not grow politely. They flared, rested, and flared again. Take a breath and picture a single newborn star cluster inside one of these distant galaxies. The cluster is cradled in gas. Massive young stars flood their neighborhood with energy. Their light carves bubbles, their winds push on the surroundings, and their short lives end in explosions that seed the area with heavier elements. Webb does not resolve each star at those distances, but it can feel their combined effect: the blue-leaning glow of youth, the emission lines from excited gas, the overall color shaped by dust. It is like hearing a choir without picking out individual voices, yet still knowing whether the singers are children or adults. Gravitational lenses add another layer of help. When a background galaxy is strongly lensed, we sometimes get multiple images of the same object. Each image takes a slightly different path through the curved space, which means the light can arrive at slightly different times. In rare cases, astronomers watch a flare repeat. That time delay becomes a ruler. It helps refine models of the lensing cluster and improve our estimates of distances and masses in the scene. So the arcs are not just pretty, they are rulers and magnifiers at once. None of this would matter without careful checking. Early claims of record-breaking distance push the edge of what is measurable, and mistakes can happen. Dust can make a closer galaxy look redder and older than it is. A sudden burst of star formation can mimic the light of a heavier system. Even a chance overlap of two faint smudges can trick the eye. This is why teams work in layers. First photometry, colors, and brightness. Then spectroscopy, precise fingerprints. And then cross-checks with other telescopes and methods. Surprise is welcome. Confirmation is vital. Let's not forget the quieter thread of exoplanets in this deep tapestry. While part of Webb stares into ancient darkness, another part watches nearby stars for slight dips in light as planets pass across. During those minutes, the instrument collects spectra, tiny notches carved by molecules in the planet's air. Water vapor shows up as a soft set of features. Methane leaves a different pattern. Carbon dioxide leaves another. Even clouds and hazes can be inferred because they blur or mute certain lines. It is careful, patient work. For now, the worlds are mostly hot and puffy, easy targets. But every success on these giants is a rehearsal for smaller, cooler worlds in the years ahead. There is also a link between galaxies and planets that is easy to overlook. The heavy elements that make rocky worlds possible only exist because earlier generations of stars lived and died. If Webb tells us the early universe churned out stars faster than we thought, it also hints that the raw materials for planets and life were set into circulation earlier. That does not mean life started early everywhere. It does mean the kitchen was stocked sooner. If the pace here feels steady, that is on purpose. This story rewards gentle attention. The early universe is not yelling. It is whispering from very far away. Webb's trick is to make the whisper audible without distorting it. Cold instruments, long exposures, careful math turned into plain conclusions. When we say, too big, too soon, what we really mean is, faster than our old models predicted. The physics is intact. Our guesses are improving. At the end of a long observing campaign, teams release images and data to the community. Students on laptops in quiet rooms, senior scientists with coffee mugs, citizen scientists at home, they all sift the same treasure. Little by little, candidates become confirmations, and a new baseline for the early cosmos takes shape. That baseline will guide the next generation of questions. How common were the first black hole seeds? How patchy was the reionization fog? How quickly did the first dust grains form? And what did that dust do to the growth of stars? Hold that deep field in your thoughts a moment longer. The arcs, the sparks, the quiet background like velvet. Somewhere in that view is a path from a time when no heavy elements existed to the time when carbon, oxygen, and iron spread through galaxies. Somewhere in that view is a hint of the first engines at galactic centers learning how to feed, and threaded through it all is gravity, doing one simple thing very well: gathering. Under the skin of those deep images lies a hidden structure, a web. Not a web of threads you can touch, but an invisible scaffold made mostly of dark matter. Think of dark matter as the quiet framework that does not shine yet shapes where everything else goes. Gravity gathers this unseen material into knots and filaments. Gas falls along those paths like rain finding riverbeds. Where the streams meet, galaxies light up. Webb's fields, full of tiny sparks, are really cross-sections of this larger pattern, the cosmic web, drawn in starlight. This framework helps solve a puzzle. How did galaxies appear so quickly? If the skeleton was already there, laid down by dark matter's gravity, then regular matter had an easy guide. It settled into the deepest pockets first, giving the earliest galaxies a head start. When you hear astronomers talk about halos, they mean those pockets, rounded regions where dark matter and gas are bound together. A halo is a cradle. Put enough gas in the cradle, cool it, and stars begin to form at a healthy pace. But star formation is not a steady faucet. It comes in pulses. A burst flares, young stars flood their neighborhoods with fierce light and wind, and then supernovae go off like timed fireworks. Those explosions push gas back out, slowing the next round of starbirth. Later, the gas cools again and drifts inward for another burst. This stop-and-go rhythm is called feedback. It keeps galaxies from using up their fuel too fast and helps explain why some early systems look compact and intense while others look quieter. Webb's spectra catch the fingerprints of these cycles: bright emission lines from energized gas during bursts and softer glows during rest. At many centers, another engine adds its own beat. A growing black hole. When gas spirals down toward the hole, it heats up and shines a lot. In its loudest phase, we call that glow a quasar, a kind of lighthouse you can see across billions of light years. Quasars in a young universe do double duty. They light up the fog around them, letting us test how clear or misty the intergalactic space still is, and they tell us how fast black holes can grow. Webb's sensitivity means we can pick out dimmer, earlier versions of these engines, long before they reach the blinding heights seen by older surveys. You might wonder how we actually tag something as young or ancient, just from a picture. The trick is to watch where the light goes missing. Hydrogen, the most common element, absorbs light blueward of a specific cutoff. In very distant galaxies, the expansion of the universe shifts that cutoff deep into the infrared. Webb looks for that sharp step, then checks with spectra to be sure. That step, plus a few well-placed lines from glowing gas, yields not only distance, but a sense of the galaxy's mood. Is it in a starburst? Is dust present? Are heavy elements common or rare? Dust itself is a surprise guest this early. Dust is made of tiny grains, carbon, silicates, metals born in the atmospheres of old stars and in supernova debris. Finding dust in very young galaxies tells us that the first stars lived and died quickly enough to enrich their homes. Dust matters because it changes what we see. It dims and reddens light, hides newborn stars, and cools gas efficiently, sometimes helping new stars form. Webb's mid-infrared eyes are particularly good at catching dust glow, turning what used to be blank darkness into warm, textured scenes. Let's press gently on the phrase, too big, too soon. Early estimates of galaxy masses rely on how bright they are at different wavelengths and on assumptions about how many small stars versus big stars they contain. If the first galaxies made proportionally more massive, short-lived stars than today, they would look very bright without being as heavy as we think. If an ongoing burst dominates the light, it can fake a higher mass. If dust is patchy, it can distort colors in ways that complicate the math. None of these possibilities are errors. They are reminders that the earliest universe may have played with the same ingredients in slightly different ratios. Webb's longer, deeper spectra help untangle those effects step by step. Another quiet helper is lensing by foreground clusters, which we touched on before. In some remarkable cases, lensing not only magnifies a background galaxy, it stretches it so much that we can see internal structure, clumps, knots, and lanes of star formation far earlier than expected. With careful modeling of the lens, astronomers reconstruct the original shape and even estimate how star formation is spread across the tiny target. It is like reading a distant sign reflected in a curved spoon, then using the spoon's shape to undistort the message. Now take a short detour from galaxies to planets, because Webb was built to do both, and the two stories rhyme. In young galaxies, we read chemistry from faint lines to learn how many generations of stars have cooked. In exoplanets, we read chemistry from faint lines to learn what a sky is made of. One of Webb's first triumphs was a crisp detection of carbon dioxide in a hot giant planet's atmosphere, a clean notch in the spectrum that older telescopes could only hint at. Since then, it has mapped water vapor on multiple worlds and started probing clouds and hazes. These are not Earth-like places yet. They are training grounds. The techniques we perfect on puffy giants will later be turned towards smaller, cooler worlds, the ones that invite the hardest questions. If this sounds slow and methodical, that is because it is. Big claims need the quiet company of careful steps. Teams release their data, skeptics poke at assumptions, and updated analyses refine the picture. For the early universe, that picture is settling into a clear theme. Rapid assembly along the cosmic web, vigorous feedback shaping the pace of starbirth, early black holes adding heat and light, and dust arriving sooner than many guessed. It is a universe in a hurry, but not a universe breaking its own rules. There is beauty in how different instruments play together. Webb brings the cold, sharp infrared view. Ground-based giants bring high-resolution spectra and can stare for nights on end at a single faint target. X-ray observatories check for the high-energy signatures of feeding black holes. Radio telescopes trace cold hydrogen, the raw fuel for star formation, and hunt the faint 21-centimeter whisper that maps the fog itself. Piece by piece, a multicolor portrait forms, and any one instrument's blind spots are covered by another's strengths. Let's bring the scale back to something you can feel. The oldest light Webb sees began its trip when there were no planets like Earth and no elements to build them with. Since then, the universe has expanded. Galaxies have collided and merged, and countless stars have lived and died. Every time you take a breath, you complete a loop that began in those early furnaces. Oxygen from ancient stars into your lungs, carbon stitched into your cells, iron moving oxygen through your blood. When we say Webb caught a galaxy at the dawn, we are also saying Webb watched a step on the path to you. What then is the shock in shocking? It is not that physics failed. It is that the universe took the opening note and rushed into a melody sooner than we scored it. We expected a slow overture. We got an early chorus. That chorus forces us to tune our instruments, adjust our timing, and listen more carefully. The reward is a cleaner song, one that still follows the rules but sings them with unexpected speed. Ahead, we will visit specific discoveries that anchor this theme. Deep fields, where dozens of early candidates became confirmed distances, lensed galaxies that reveal their inner knots, and quiet spectra from planets that carry the faint taste of water and carbon. We will keep the language plain, the steps patient, and the wonder steady. The night is vast, but the story is readable. Webb is turning the oldest whisper into a voice we can finally hear. Before we dive deeper into results, let's meet the tools that made them possible. Webb carries 3 workhorses tuned to different shades of invisible light. First is NIRCam, the near-infrared camera. Think of it as the wide, sharp eye that maps a scene and picks out the faintest specks. It uses a set of filters to isolate narrow slices of color, helping us sort nearby objects from ancient ones. When people talk about deep fields, most of the crisp star fields and tiny galaxies you see began as NIRCam images stacked over many hours. Next is NIRSpec, the near-infrared spectrograph. Pictures tell you where, spectra tell you what. NIRSpec can place hundreds of tiny shutters, little doors that open and close, so it can take many spectra at once. Each spectrum is a thin barcode of light that reveals distance, motion, and chemistry. This is how early candidates stop being maybes and become measured galaxies. The last of the trio is MIRI, the mid-infrared instrument. It sees longer wavelengths, where warm dust and complex molecules glow. MIRI needs a special refrigerator to stay ultra-cold, and when it works, dusty nurseries and hidden cores leap out of the darkness. Turning raw data into the images you know is an art with rules. Detectors pick up cosmic rays, tiny sparks from high-energy particles that must be identified and removed. Slight variations in pixel response get flattened, so one part of the image isn't falsely brighter than another. The telescope shifts its aim between exposures in a planned pattern called dithering. That fills in gaps, averages out defects, and sharpens detail when the frames are combined. Only after all that cleaning do the faintest objects stand up from the noise. Colors in Webb pictures are carefully chosen. Infrared light is invisible to our eyes, so teams assign visible colors to different filters. Longer wavelengths are mapped to redder tones, shorter ones to bluer tones. This isn't decoration, it's translation. A reddish galaxy in a deep field often means we are seeing very stretched, very old light. A bluish knot can signal a burst of young, hot stars. Once you learn this language, the pictures read like a weather map of the early cosmos. Distances come in two flavors. Photometric redshifts are quick estimates based on how an object's brightness drops across several filters. They are fast and good for finding candidates, but they can be fooled by dust or unusual star mixes. Spectroscopic redshifts are slower but precise. They pin down the exact shift of known lines, hydrogen, oxygen, carbon, so the distance is anchored. The story of Webb's too-soon galaxies began with photometric hints and has been tightening with more spectroscopy over time. The pattern remains. Many compact active systems show up earlier than expected, even as individual masses get revised. About those black holes, older than time itself, that phrase is poetic, not literal. Nothing is older than time. The surprise is that some black holes appear very massive when the universe was still young. If you start with a seed a few hundred or a few thousand times the sun's mass and feed it efficiently, continuously pulling in gas, it can grow fast. If, in rare places, an enormous gas cloud collapsed directly into a black hole, tens of thousands of times the sun's mass, the head start is larger. Webb's job is to catch the glow around these engines and weigh their influence on the galaxies that host them. One steady theme in the data is feedback, the push and pull between stars, gas, dust, and black holes. When many massive stars form together, their light and winds heat and stir the surrounding gas. Supernovae add shock waves and heavy elements. A feeding black hole can blow powerful outflows that either clear the central region or compress gas on the edges, sparking new starbirth. Webb sees feedback in bright emission lines from energized gas, in the shapes of dusty cavities, and in how star formation is arranged in clumps and rings. Early galaxies do not grow on a smooth curve, they pulse. There are also quiet technical hurdles that teams watch for. Detectors can retain a faint memory of bright objects' persistence that must be corrected. Saturated stars can leave artifacts that mimic small galaxies if not handled. Foreground objects can align just so and lens background galaxies, making them look larger and brighter than they truly are. None of these issues break the science. They simply demand careful processing and cross-checks. The more eyes on the data, the cleaner the results become. Exoplanet work follows the same discipline. When a planet transits its star, the change in light is tiny. Webb must subtract the instrument's own breathing and the star's small flickers to reveal the equally small signature of the planet's air. Success looks like shallow notches at the expected wavelengths for water, methane, or carbon dioxide. Clouds can flatten those features, telling us about particle sizes in the haze. Heat maps during secondary eclipses when the planet slips behind the star trace day-night temperature patterns. Each measurement is a stepping stone toward reading cooler, smaller worlds later. So what is the headline after these early seasons? The cosmic web offered early shortcuts. Gas fell quickly into the deepest pockets. Star formation turned on in concentrated bursts. Dust appeared sooner than we thought, meaning the first stars lived and died on tight schedules. Black holes started small but not tiny, and some fed with remarkable efficiency. Put together, the early universe looks busy, not broken, eager rather than impossible. We will soon focus on a few anchor scenes. A lensed galaxy stretched into a thin arc that reveals its inner knots. A deep field where dozens of high redshift candidates survive the hardest checks. And a hot, puffy planet whose spectrum reads like a perfect lab example. Each scene will be a calm walk. What was measured, how it was checked, what it means, and where the uncertainties still live. No rush. Clear steps, honest wonder. For tonight, hold one simple picture. An ultra-cold mirror in deep space, listening to warm whispers from a very young universe. Those whispers do not rewrite physics. They rewrite our timeline. And that, gently, changes everything. Choose one clear path from hint to proof. In a deep field, teams tagged a tiny red ember. Its brightness dropped sharply at one filter, the classic sign that neutral hydrogen was blocking bluer light, and that cosmic expansion had stretched the glow. Photometry whispered, very far. That was only the start. The spectrograph's micro-shutters opened on that dot, and the telescope held its aim for hours. In the final spectrum, a clean step and a few razor-thin lines landed exactly where they should. Distance confirmed, the candidate became real. A compact galaxy shining when the universe was still young. A measured distance invites the next question. How busy is this system right now? The answer lives in the lines. Narrow, bright emissions from hydrogen and oxygen mean hot, massive newborn stars are flooding nearby gas with energy. If the lines are broadened or shifted, winds or outflows are pushing hard. If the faint light between the lines leans blue, the stars are young. If it leans red, either older stars dominate or dust is at work. No single clue shouts. Together, they sketch a mood. A small galaxy running hot, building stars at a brisk pace. Now pivot to a second anchor scene. A background galaxy stretched into a graceful arc by a massive cluster in front of it. The arc is a gift. It magnifies the view and stretches the target so clumps inside become separable. In the reconstructed image, the galaxy breaks into neighborhoods of star formation. Some are compact and intense, others look diffuse, as if the music paused there. By sliding a narrow slit along the arc and reading how the spectrum changes, astronomers map where winds push outward and where gas is falling back in. The arc turns a distant dot into a working map. Dust matters more than many expected at these ages. In the mid-infrared, warm dust glows with a soft, steady light. Those grains were forged in short-lived giant stars and in supernova debris. Seeing strong dust signatures this early means the first stellar generations lived, died, and recycled material quickly. Dust also cools gas by radiating heat, letting clouds collapse more easily. So dust both hides part of the light we count and speeds the very process that makes new stars. Webb's mid-infrared images turn that idea into visible structure, dark lanes, warm patches, and hidden cores that shorter wavelengths miss. Black holes thread through both anchors. In some spectra, a subtle excess of light or faint high-energy clues point to an active nucleus at the center. It may not yet be a blinding quasar, but it is there, nibbling at nearby gas. Early feeding reshapes the neighborhood. It can clear the middle, leaving a ring where stars ignite along the edges, or it can stir the gas enough to trigger fresh bursts. Webb's role is to spot these hints and weigh how strong they are compared to surrounding star formation. The picture that emerges is not chaos, but a city with zoning, quiet districts, busy cores, and winds that act like changing traffic. Shift focus for a moment to a nearby star and a hot, puffy planet. As the planet transits, the star dims by a tiny fraction. During those minutes, Webb gathers spectra so clean that the atmosphere's chemistry leaves crisp fingerprints. Water vapor draws gentle notches, carbon dioxide cuts a clean groove, and methane writes a pattern of its own. When the planet slips behind the star, the total light drops again. That difference maps the dayside heat. Put the pieces together and you get a crude weather report, temperature, clouds, or haze, and which molecules are most common. These giants are not Earth-like, and that is fine. Mastering clear signals now teaches us how to read the fainter ones later. These scenes, distant arcs, tight starbursts, dusty lanes, whispering planets point to one theme. The early universe assembled structure quickly along the dark matter web and then sculpted it with feedback. Star formation came in pulses, not a gentle drizzle. Dust appeared early, speeding, cooling, and hiding some of the light we first tried to add up. Black holes were present soon enough to influence their hosts. None of this demands new physics. It demands better timing, cleaner accounting, and longer exposures. Method matters, so a word on discipline. Teams publish their processing steps and share code. They release raw and cleaned data so others can test assumptions. Photometric estimates are labeled as candidates until spectra arrive. When masses are revised downward, because a short-lived burst made a galaxy look heavier than it is, that update is logged as progress, not failure. This culture is how shocking turns into understood. Wonder stays. Claims become sturdy. For scale you can feel. Compress cosmic time into a single human life. If the first bright knots Webb sees lit up in year 1, the sun would form around year 9, Earth a little later, and humans would appear in the last seconds before midnight. Yet the photons from those year 1 cities have been traveling the whole time, threading their way through expanding space to reach a mirror we unfolded only yesterday. Catching them ties our moment to theirs with a straight line of light. Where do we go next? Deeper exposures in the same fields will turn maybes into measurements. Wider surveys will map how common these compact, busy galaxies really were. Coordinated observations, infrared, optical, radio, and X-ray, will watch the same targets with different senses, covering each instrument's blind spots. On the planetary side, the push is toward cooler sub-Neptunes and super-Earths around small, quiet stars, where atmospheric signals are faint but within reach. Each step is modest alone. Together, they turn surprise into a timeline we can trust. Hold a few simple pictures as you drift: the thin rainbow lines that pin a distance, the stretched arc that turns a dot into a map, the warm dust glow that proves quick recycling, and the tiny dip in a star's light that betrays a planet's air. This is the sound of the early universe becoming legible. It is not a shout, it is a steady voice, carried across 13 billion light-years, speaking clearly through gold and cold. Start with the faintest kind of cartography, tracing how a light-blocking fog became see-through. In the first few 100 million years, space was filled with thin, neutral hydrogen that swallowed specific colors, especially the sharp Lyman-α line of hydrogen. As the first stars and black holes lit up, their energy carved clear bubbles in the mist. Stitch enough bubbles together and the universe turned transparent to starlight. Webb does not see the fog directly, it sees whether light makes it through. When Lyman-α arrives intact, a bubble likely stands between us and the source. When it is muted or missing, neutral gas is still in the way. Two beacons guide this work. One is galaxies whose spectra show strong Lyman-α emission, a sign their light found a clear path. Think of them as windows. The other is quasars, the bright feeding phases of young black holes. As quasar light crosses intergalactic space, every patch of neutral hydrogen bites a little out of the spectrum, leaving a forest of absorption lines. The forest sketches how patchy the fog remains at different times. Webb supplies the distances and the context: which galaxies live near which gaps, how dusty they are, and how vigorously they form stars. Gravity adds a helpful twist. Foreground clusters can lens a background galaxy, boosting and stretching it enough for clean spectra that would otherwise be out of reach. A strong Lyman-α line suggests a clear bubble. A weak one points to an edge, a missing line. Paired with other signals of youth, hints that the galaxy sits inside thicker fog. Each case becomes a pin on the reionization map. With enough pins, a timeline emerges: small bubbles, merging networks, and finally wide-open intergalactic space. Teams then turn scattered sightlines into statistics. They gather many galaxies at nearly the same distance and measure how often Lyman-α gets through. High pass rates mean cleared regions, low rates mean lingering mist. Season by season, the data outline a sequence that already looks consistent. By a few 100 million years after the Big Bang, patches of the sky were largely clear, while others were still dimmed. Webb's sensitivity makes this possible because it reaches faint galaxies that earlier telescopes could barely register. Meanwhile, radio arrays on Earth chase the 21-centimeter whisper from hydrogen's spin-flip transition. That signal should trace the fog directly, but it is faint and tangled in nearer radio noise. As those maps sharpen, they will show the fog's large-scale texture, while Webb keeps tagging where the early lights live. Cross-matching the two radio maps of the fog and infrared maps of galaxies will say not just when reionization finished, but which neighborhoods finished first and why. Energy sources leave telling signatures. If star formation drives the clearing, certain ratios of emission lines match hot, young stellar populations. If active black holes contribute heavily, high ionization lines grow stronger, and X-ray observatories should catch their glow. Early indications suggest stars carried most of the load, with black holes adding local muscle in some neighborhoods. That balance matters because it sets the pace for heating and chemistry in the young universe, influencing how quickly gas cools and collapses into new generations of stars. Dust complicates and enriches the view. Even a little dust can scatter Lyman-α, making a clear region look cloudy. Webb's mid-infrared images detect dust glow directly, letting teams flag where dust, not distance, is muting the signal. Dust also cools gas efficiently, helping new stars form. Finding dust so early implies that the first stellar generations lived, died, and recycled material quickly. In pictures, this shows up as warm patches, dark lanes, and hidden cores that shorter wavelength cameras miss. To keep estimates honest, observers measure not just lines but the starlight between them, the continuum. Its shape hints at the mix of ages, dust content, and the production rate of ionizing photons. Those numbers feed models of how easily photons leak out of galaxies. The early surprise is how many compact, efficient systems seem to be strong leakers. That helps explain the quick clearing without asking for exotic physics. It is ordinary ingredients used at brisk tempo. Environment is another lever. Galaxies are not sprinkled at random. They gather in groups along the dark matter web. In dense regions, reionization can finish early because many sources cooperate and their bubbles merge. In sparse regions, pockets of fog hang on. Webb's wide but deep mosaics let teams compare these neighborhoods. The emerging pattern looks like an uneven sunrise, clear patches beside valleys where mist lingers, all moving toward transparency, but not in lockstep. Even with this progress, caution rules. Photometric distances can promote an object into the very early group by mistake if dust or unusual stars skew the colors, or if lensing makes a galaxy look older and heavier than it is. Spectroscopic checks thin the roster. Several headline objects have seen their masses revised downward once deeper data arrived. That is not a retreat. It is refinement. A lean, well-measured census is stronger than a generous, uncertain one. So, does shocking still apply? Yes, in the right sense. The shock is timing. Dark matter laid the tracks early. Gravity moved gas along them efficiently. Stars lit the stations in tight bursts. Black holes ran some hot junctions. Dust arrived sooner than expected, acting as both veil and coolant. The laws held, the schedule tightened. That is a rich surprise. Not a broken frame. Bring the scale back to a human room. A single photon captured by Webb tonight may have started out when no Milky Way-like galaxies existed. It crossed expanding space, skirted clusters that bent it, threaded past tiny grains of dust, and ended as a few electrons in a detector colder than ice. Those electrons become a line on a graph. The line becomes a distance. The distance becomes a date on the universe's calendar. From that date, we rewrite a paragraph in the origin story without changing the laws that wrote the book. As we move on, the plan stays careful and calm. We will look at a deep field that shows an uneven sunrise, a lensed arc that turned a single sight line into a neighborhood, and an exoplanet spectrum that reads like clean handwriting. Each case says the same thing in a different accent. The early universe was busy, not broken. The rules held, the tempo surprised. Thanks to an ultra-cold mirror far from Earth, the oldest notes are now clear enough for anyone to follow, even with their eyes closed. Take one well-studied patch of sky. To the eye, it is mostly black, scattered with a few crisp stars from our own galaxy. Through Webb, the black turns busy. Specks become systems. Colors stretch warm, hinting at great distance. Teams grid this patch like a quiet city map, labeling each faint glow with coordinates, brightness, and quick distance estimates from color. The next step is patience. They schedule repeat visits, rotate filters, and return with near-spec to open the micro-shutters on the best candidates. Hours pass in steady stares. Later, on Earth, the thin rainbows arrive. Some candidates fall away, others hold up, and the picture of a crowded early universe gets sharper. Now focus on structure inside a single distant galaxy. Even when it remains a dot for us, the spectrum weaves a narrative. Strong hydrogen lines say young stars are burning hot. Oxygen lines reveal how much chemical seasoning the galaxy has gained from previous star generations. The overall slope of the starlight shows whether dust is softening the blue edge. A slight tilt or broadening hints at winds that are moving fast enough to reshape the neighborhood. Stitch those clues together and you get a living scene. Clumps of birth, cavities of cleared gas, and the first signs of a central engine learning to eat. Star formation often shows up as rhythm rather than a straight climb. A burst lights the region, radiation and winds push back, and supernovae punch holes. Gas cools on the edges, flows inward, and the next burst begins. Webb catches these cycles in multiple ways. Blue-leaning continua from young populations, bright emission from energized gas, and mid-infrared warmth from dust that both hides and helps. The early universe looks less like a quiet drizzle and more like coastal wave sets of energy arriving, retreating, and arriving again. Dark matter provides the stage. Call it the scaffolding that never shines. Simulations long predicted that it would gather into halos early, drawing in regular matter along invisible filaments. Webb's census of compact active galaxies at great distances fits that script. When the skeletal framework is deep, gas finds the low places quickly, and stars switch on. The surprise is not the existence of the web, but the speed with which the lights came up along it. Add lensing and the stage gains spotlights. A massive cluster in front bends space like a glass paperweight, magnifying a background galaxy into a fine arc. Suddenly, interior knots separate. With thoughtful modeling of the lens, astronomers reconstruct the original shape and map the locations of the brightest clumps. In a few gems, time delays between multiple lensed images even offer a second ruler. The same flare repeats after a calculable pause, tightening both the mass model of the lens and the distance of the source. Nature, in those cases, lends a telescope to the telescope. What about black holes? In the nearby universe, nearly every big galaxy hosts one at its core. Webb's early view implies that seeds for those cores appeared early and grew quickly in at least some neighborhoods. Two routes remain on the table. 1. Heavy first-generation stars collapsed, leaving seeds that aided a disciplined, near-continuous pace. 2. In rare conditions, a huge cloud fell straight in before it could fragment, creating a larger seed that needed less time to become massive. Webb cannot watch the birth, but it can weigh the consequences: the heated gas, the compact central light, the spectral signs of an engine in training. Reionization, the clearing of the cosmic fog, threads through all of this. A galaxy's Lyman-α line is a weather vane. If it arrives strong, a bubble of clear space likely surrounds the source. If it's muted, fog still lingers. Gather hundreds of such weather vanes at similar distances, and the patchwork of clearings becomes a map. Early results, strengthened by Webb's reach, suggest an uneven sunrise. Some regions bright and breathable, while others remain hazy, all moving toward clarity but not on the same clock. Dust appears sooner than many expected. Tiny grains of carbon, silicates, and metals glow in the mid-infrared and darken the blue light we otherwise count. Their presence means that first stars lived fast, died fast, and recycled material efficiently. Dust cools gas, allowing it to collapse into new stars. It also hides some of the newborns from view. In practice, that means we must correct both for missing light and for accelerated star formation. Webb's combination of near and mid-infrared eyes makes those corrections less guesswork and more measurement. Lest this sound like a tidy story, remember the guardrails. Photometric distances can mislead when dust, odd stellar mixes, or lensing distort colors. Spectroscopic checks are the remedy. Some headline masses have indeed been revised downward as deeper spectra arrived. That is healthy. A sturdy, lean early census is more valuable than a bloated one full of maybes. In science, trimming is a form of growth. While galaxies tell us how the universe assembled, exoplanets tell us what distant places feel like. Webb has already read clean carbon dioxide in a hot giant sky and mapped water vapor in others. It has begun to infer clouds and hazes and to sketch temperature contrasts between day and night on worlds scorched by close orbits. These are the easy wins by design. The practice they give controlling for instrument drift, star spots, and subtle systematics prepares the field for cooler, smaller planets, where the signals are faint but the stakes are personal. Tie those threads together, and a theme emerges. The early universe did not idle. Guided by the dark matter web, gas pooled quickly, star formation ignited in pulses. Dust joined the party early, both veiling and enabling growth. Black holes arrived soon enough to shape their streets. The fog lifted in patches that merged over time. None of this breaks the rules. It compresses the schedule. Bring the scale back home. If you stretch the universe's history across a single long night, the first compact galaxies Webb confirms appear in the dark hours before dawn. Our sun rises close to morning. Humans arrive in the last sparks before sunrise, yet the photons from those early hours travel the whole night to reach us now, carrying steady hints about tempo and texture. We built a mirror, sent it to cold space, and tuned it to hear those hints. The result is not chaos, it is a sharper calendar. In the next section, we will slow down with 3 calm case studies. A lensed arc that reveals star-forming knots across a tiny disk, a deep field whose candidates survived the hardest spectroscopic tests, and a hot planet spectrum that reads like a textbook example of clean chemistry. Each will be a quiet walk. What was seen, how it was checked, what it means, and where the uncertainties still live. Gentle pace, plain words, clear wonder. Case Study 1. The Stretched Galaxy. In one survey, a massive foreground cluster bent spacetime enough to magnify a tiny background galaxy into a thin arc. The team modeled the cluster like a layered glass sculpture, measuring how each clump of mass deflected passing light. With the distortion unraveled, the arc resolved into a compact disk, only a few hundred light-years across, tiny, next to the Milky Way, but burning fast. NIRSpec traced sharp hydrogen and oxygen lines along the arc, and their slight shifts mapped motions inside. Star-forming clumps, winds pushing outward, calmer lanes where gas was falling back in. MIRI added the glow of warm dust, proving that short-lived giant stars had already lived and died there. The lesson was simple and strong. Even the earliest small disks were clumpy, intense, and already recycling their gas. Case Study 2. The hard-won deep field. Another program chose patience over spectacle. Instead of one marathon stare, it returned to the same quiet patch many times, rotating filters and stacking exposures. Photometry flagged dozens of very red candidates, the signature of ancient, stretched light. Then came the careful part. Open the micro shutters on the best targets, hold steady, and let thin rainbows build until they spoke clearly. Several candidates dropped out, dusty interlopers closer than they looked, or blended sources masquerading as one. But a sturdy handful survived the hardest checks. Their spectra showed the textbook step from hydrogen absorption and clean emission lines at the expected places. Taken together, they pushed the census toward a clear pattern. Compact, busy galaxies were common earlier than we penciled in. That does not break physics. It tightens the schedule for how quickly gas settled into deep pockets of the dark matter web and how soon the fog of neutral hydrogen began to clear. Case Study 3. The textbook planet. While half of the observatory chased ancient galaxies, the other half watched a nearby star with a puffy hot Jupiter. The plan was strict. Record the star's spectrum before transit, during transit, and again when the planet slipped behind the star. Model and remove the instrument's own breathing and the star's tiny flickers. What remained were crisp atmospheric fingerprints, a strong carbon dioxide notch, broad water features, and muted methane, likely flattened by high clouds or hazes. A small drop in total light when the planet hid behind the star drew a rough heat map of its day side. No, this world is not Earth-like. That is the point. Getting a perfect lab example on an easy target proves the method and trains the field for cooler, smaller worlds where signals are faint and the stakes are personal. All three scenes rhyme in how they were built. In the lens dark, the mass model was tested against multiple images and, where available, short time delays between mirrored flares, not just one pretty curve. In the deep field, color alone did not crown a record. Thin spectral lines had to speak. In the planet case, the team published the detrending steps that turned raw counts into a clean spectrum before naming a molecule. The shared result is sturdy knowledge. Surprise lives on, but it stands on reinforced floors. They also rhyme in scale. The arc shows structure across a few hundred light-years when galaxies were toddlers. The deep field turns millions of light-years into population statistics, pushing us past anecdotes. The planet compresses everything to a sky only a few scale heights thick, yet still readable from light-years away. Webb binds these scales with the same approach. Ultra-cold instruments listening to faint infrared whispers, then a community that checks, repeats, and corrects. Why this matters to the larger story. The arc proves that early disks could be clumpy and intense, with winds already moving gas around. The deep field proves that such systems were common enough to clear the cosmic fog faster than we expected and to seed heavier elements sooner. The planet proves that high-precision spectral reading is mature now, ready to move from hot giants to cooler sub-Neptunes and super-Earths. Each case narrows uncertainty without asking for new laws. Cautions remain in view. Lensing can hide traps. A mismodeled mass clump can overstate magnification and trick us about true size and brightness. Deep field completeness is tricky. Faint galaxies with unusual star mixes can evade cuts. Transit spectra can be flattened by clouds and hazes, biasing molecule estimates. Each caution has an antidote. Better lens maps anchored by more multiple images, deeper exposures with broader filter sets, and time series observations long enough to separate weather from instrument drift. As those antidotes are applied, the picture sharpens without becoming louder. Step back and the message is simple. The early universe did not dawdle. Dark matter laid a scaffold. Gravity funneled gas along its ribs. Stars ignited in bursts. Dust arrived early. Small black holes learned to feed, and wide regions cleared sooner than expected. Our models are not wrong. They were under-energized, We update star formation recipes, dust treatments, and the mix of stellar masses at the dawn. The score stays the same. The tempo increases. Hold one last thought before we move on. These results do not rewrite the fundamentals. They ask us to write a crisper schedule and keep our words plain. Too big, too soon becomes faster assembly with strong feedback. Impossible black holes becomes larger seeds and efficient feeding in rare pockets. Shocking signals from rogue worlds becomes clean fingerprints and heat maps on. Giants as rehearsal for smaller targets. Simple phrases, honest to the data. Ahead, we will fold in two more anchors, a quasar lighting its neighborhood like a lighthouse at dawn, and a lensed supernova whose echoed flashes give a direct handle on distance. Together with tonight's three, they round out a calm, evidence-first picture. Busy, not broken. Quick, not lawless. Readable, not forbidding. The sky is vast, but the path through it is being marked with steady lights. Lighthouse first. A quasar is a young galaxy's central black hole in a loud feeding phase. Gas spirals inward, heats, and blazes so fiercely that the core can outshine its entire host. In the early universe, a quasar does more than glow. It hollows a clear bubble in the surrounding fog of hydrogen. Astronomers read that bubble in the quasar's spectrum. Close to the source, the signal looks clean because nearby hydrogen has been stripped of electrons. Farther out, a gentle damping wing appears where neutral hydrogen still absorbs light. The size and shape of these features tell us how transparent the neighborhood is and how quickly the fog is lifting. Webb's strength is catching the faintest, farthest of these lighthouses and measuring their surroundings in detail. When the spectrum also shows thin lines from oxygen, carbon, or silicon, we learn that several generations of stars have already lived and died there, spreading heavier elements. That is a lot of chemical work done early. The rise and width of the quasar's broad lines reveal how fast gas is whipping around the black hole, offering a mass estimate for the central engine. The surprise is not that black holes existed, then gravity guarantees that, but that some had already grown to impressive sizes. That pushes us to ask whether their seeds were born large or whether feeding was exceptionally efficient. Different beacon, different clock, a lensed supernova. When a massive cluster sits between us and a faraway galaxy, its gravity bends space enough to produce more than graceful arcs. If a star in the background galaxy explodes, multiple copies of the same supernova can appear at different spots in the lens, each one brightening and fading with a slight delay. The light paths are unequal corridors. Watch the echoes and you test the lens mass model, anchor the delays with careful calibration, and you add a clean distance marker to the cosmic timeline. Webb improves this technique in two ways. First, its sharp infrared vision finds supernova flashes behind dusty, distant lenses that older telescopes missed. Second, its steady photometry tracks the rise and fade accurately across weeks and months, even when each image is faint. Each new lensed supernova becomes both a physics lab and a ruler. It cross-checks how matter visible and dark is arranged in the lens, and it adds a timed mark on the universe's distance scale without leaning only on standard candles. Put these beacons together and they speak the same language. Quasars light up nearby fog and weigh early black holes. Lensed supernovae echo through curved space and reveal how foreground mass is arranged. Both feed the larger story. Rapid build-out along the dark matter web, early engines switching on, and gravity curving the paths by which their light reaches us. Now add a quieter but telling thread, the chemistry of the interstellar medium in very young galaxies. Webb's mid-infrared instrument sees the glow from tiny dust grains and from molecules like PAH's polycyclic aromatic hydrocarbons that light up when starlight tickles them. Finding PAH-like features early suggests the carbon cycle was running briskly, primed by short-lived massive stars. Pair that glow with near-infrared oxygen lines, and you can estimate how enriched a newborn galaxy has become. The tally so far points to quick recycling. Stars form, explode, and seed their homes with heavier elements on tight schedules. Seeds for early black holes remain under debate, and Webb constrains, if not witnesses, their births. Two routes likely operate. One starts with very massive, metal-poor stars that collapse into black holes hundreds of times the sun's mass. Then accrete gas steadily near the allowed limit. The other demands special conditions. A pristine, dense gas cloud that stays hot enough to avoid fragmenting into many stars, and instead collapses directly into a black hole tens of thousands of solar masses. Webb cannot film the instant of birth, but it can weigh the consequences: broad emission lines, hot dust near the core, and signs that gas is being heated and pushed around, then compare those clues to models of each path. Caution keeps the picture honest. Quasar light can trick us if dust along the way reddens it or if the host galaxy adds more to the spectrum than assumed. Supernova lenses can be mismodeled if unknown clumps of matter sit along the path. Teams answer with redundancy. Analyze multiple lines together, build independent lens reconstructions, and cross-check with X-ray and radio observatories that see different parts of the same drama. What survives these checks is sturdier than any single beautiful image. The human-scale payoff is perspective. A quasar's bubble and damping wing, a supernova's echoed flashes, a dust feature's soft rise. These are modest signals etched on nearly invisible light. Yet from them we infer timelines. When the fog cleared, how quickly black holes grew, how fast the first heavy elements spread. No single measurement carries the weight. The ensemble does. It is science's harmony rather than solo. Keep one eye on what comes next. Wider Webb mosaics will search systematically for the faintest quasars at early times, mapping how common they were and how much they contributed to clearing the fog. Dedicated programs will patrol strong lens clusters for fresh supernovae, ready to catch the first image and then wait patiently for the delayed copies. Meanwhile, deeper integrations on dusty, compact galaxies will refine dust chemistry and star formation histories, turning broad themes into calibrated numbers. Each piece sharpens the calendar of beginnings. All of this loops back to the headline that sounded dramatic at first: shocking results. The shock is not rebellion, it is urgency. The early universe built structure on a tight schedule, and these beacons help mark the hours. Quasars say, engines on. Lensed supernovae say, paths curved. Dust features say, recycling already. The melody is faster than our old sheet music, but it remains the same song. For a last, quiet scale, think about the time it takes in your own life to form a habit. Once a path is worn, each step is easier. The cosmos seems to have worn its first paths quickly. Dark matter laid grooves, gas rushed in, stars flared and reset the stage, and central engines learned to feed. Webb's gift is to show these first habits not as legend, but as light measured, cleaned, and shared. From there, a clearer calendar of beginnings takes shape, one careful spectrum at a time. Another thread tying the story together is timekeeping. To say a galaxy is young or ancient, we need more than distance. We need clocks. Light gives us several. One clock is the color of a galaxy's stars. Blue-leaning light means many massive, short-lived stars are present now, so the last burst of star formation was recent. Redder, smoother light points to older population. A second clock is chemistry. The first stars forged heavier elements, carbon, oxygen, iron, and scattered them when they died. Measuring those elements tells us how many stellar generations have passed. A third clock is dust. Its presence and temperature reveal how quickly recycling has happened. Webb reads all three at once, turning a faint smudge into a dated page of cosmic history. With those clocks in hand, we can talk about efficiency without math. Think of two kitchens with the same ingredients. One turns out meals slowly, the other plates dish after dish. Early compact galaxies look like the busy kitchen. They convert gas into stars at a higher pace for short spurts, then rest as feedback pushes gas outward, then start again when the gas cools. This stop-go rhythm keeps showing up in Webb spectra. Bright lines from excited gas during the cook, softer continua during recovery, and mid-infrared warmth from dust that remembers the heat. There is a tempting shortcut to declare the early kitchen different ingredients and be done. But the honest answer is subtler. The ingredients are the same: hydrogen, helium, gravity, radiation, time. The recipe is being tweaked. Maybe early star clusters formed proportionally more massive stars than we see today. Maybe gas clouds were denser and collapsed more cleanly along the dark matter web. Maybe mergers were more common and delivered fuel on tight schedules. Webb cannot settle every maybe alone, yet it trims the list by replacing guesses with measurements. Black holes are part of the timetable too. When a central engine switches on, it is not just scenery, it changes the neighborhood. Gas heats, outflows carve channels. Inflow is redirected. Webb sees these shifts as widened lines, central compact light, and warm dust near the core. The practical question is not, how big can a black hole get? But how soon did it matter? Early answers point to early enough present in some galaxies when the universe was still shaking off its fog. Two quiet tools help keep us honest about mass and pace. The first is surface brightness, the simple fact that light spreads out and dims with distance. Webb sensitivity lifts that handicap, but it does not erase it. Teams correct carefully so a faint extended glow is not undercounted. The second is completeness. How many objects you miss because they are too dim, too dusty, or too oddly colored for a quick search to catch. Deep programs now build in blind steps that do not pre-screen on color, then compare results. Where the two approaches agree, confidence rises. Where they diverge, the hunt continues until the gap is explained. Gamma-ray bursts and supernovae add more clocks. A long gamma-ray burst marks the death of a massive star and briefly turns its host galaxy into a spotlight. Catching the afterglow with Webb gives a precise distance and a peek at the host's chemistry. Supernovae, especially when lensed, offer both timing and a test of how matter sits between us and the source. These transients are rare at great distance, but each one is a sharp pin in the timeline. Exoplanets keep pace in their own quiet lane. Once a team nails water, carbon dioxide, and methane on the easy giants, it can push toward smaller, cooler worlds around dimmer stars. The signals shrink, but the method holds. Measure before, during, and after transit. Clean the instrument's breathing. Compare to a library of molecular fingerprints. Even non-detections help. If expected features are missing or flattened, that tells you clouds or hazes are thick, or that a different molecule dominates. The goal is not a headline claim. It is a catalog you can trust. A word on language. Phrases like too big, too soon, and older than time grab attention, but can mislead. What Webb shows is faster assembly, not broken rules. It shows early black holes, not violations of cause and effect. The right phrases are plainer. Efficient star formation in compact halos, quick recycling into dust, early activation of central engines, patchy, accelerating reionization. Simple words fit the data and travel well from paper to pillow. Another steady theme is cross-checks. Infrared maps where the oldest light lives. Optical telescopes refine structure in nearer hosts. X-ray observatories flag feeding black holes. Radio arrays chase the 21-centimeter whisper of neutral hydrogen and the cold gas that feeds galaxies. Each wavelength is a sense. No single sense is enough. Webb's biggest cultural contribution may be this habit of ensemble seeing. Share the data, layer the views, tighten the claims. You may wonder where theory sits in all this. Simulations have long predicted a cosmic web, bursty star formation, and feedback that regulates growth. The tension was timing. Some popular models scheduled the first crowded city blocks later than the sky is now showing. That is not a crisis. It is a patch. Update the star formation recipes. Allow for earlier dust. Try a slightly different mix of stellar masses in newborn clusters, and the curves move closer to the measurements. Theories that bend toward data survive. Those that cannot will be replaced. Looking ahead without hype is easy. More time on the same deep fields will turn thin hints into thick spectra. Wider, shallower mosaics will show whether the dense early pockets were rare jewels or typical neighborhoods. Targeted lens patrols will catch more echoed supernovae and faint arcs that expose internal knots. On the planet side, repeated transits on a short list of small, quiet stars will stack signal until first tastes of sub-Neptune and super-Earth atmospheres emerge with confidence. Each step is incremental. The total is transformative. Bring it back to a room at night. A gold-plated mirror sits 1,000,000 miles out, colder than ice, holding still. From your side, the work is simple. Breathe slowly, let the story flow. A field that looked empty now holds hundreds of galaxies. A dot that looked smooth now shows clumps and winds. A star that seemed steady hides a planet with water in its sky. None of this requires you to juggle math. It asks only for patience and a willingness to let faint signals add up. If a single sentence must carry this section, let it be this: the early universe was busy, not broken, and Webb is turning that busyness into a dated, readable story. The clocks agree more each season. Colors, chemistry, dust, transients, lensed echoes. They point to a schedule with less idle time and more early work. That is a surprise worth having. It does not tear pages from the physics book. It writes annotations in the margins we should have filled sooner. We will next settle into one deep field in detail, walking row by row through how candidates were found, why some fell away, and how the survivors anchor the calendar. No rush, clear steps, quiet confidence. The sky is vast, but the path is marked. Begin with the field itself. Teams choose a patch of sky with little foreground dust, few bright Milky Way stars, and reliable guide stars for steady pointing. They cross-check older Hubble and ground-based maps, then lock in a mosaic that covers the area with overlapping tiles. Each tile gets a quiet plan: which NIRCam filters to use, how long for each, where to place short dithers to fill detector gaps, and when to include MIRI exposures for dust. The schedule looks calm on paper, but every exposure is doing a specific job that will matter later. Detection comes next. Raw frames are cleaned of cosmic ray hits, aligned and stacked. Software searches for faint sources just above the noise floor, measuring brightness in each filter with matched apertures. Objects are flagged if they sit near a diffraction spike or a detector edge. The first catalog is deliberately generous. It is better to include doubtful specks now and trim later than to miss a real galaxy that only barely clears the noise. Selection narrows the crowd. Teams look for a specific color pattern, a strong drop between two adjacent filters, the telltale hydrogen cutoff, and consistent faintness in the bluer bands. They compare those colors to libraries of galaxies and stars to estimate a photometric redshift. Candidates that look slightly extended tiny fuzzballs rather than pinpoints earn extra weight. Anything that matches the colors of a cool red dwarf star in our own galaxy is marked as a likely contaminant and moved aside. Quality control trims again. Sources seen in only a single filter are rechecked for artifacts. Blends are split by modeling overlapping light profiles. If a foreground galaxy might be lensing a background one, a lens flag is added so later mass modeling can correct the magnification. At this stage, the catalog holds a ranked short list. The most promising early galaxies ready for spectra. Spectroscopy is the decisive step. NIRSpec's micro-shutters open on dozens of targets, and the telescope holds steady for long integrations. In the final spectra, a clean hydrogen cutoff fixes distance. Emission lines from hydrogen and oxygen sketch the pace of star formation and the state of the gas. The overall slope of the starlight hints at dust. Objects that fail to show clear features go to the maybe later pile. The rest become anchors on the timeline. Turning spectra into physical pictures takes care. Stellar masses come from fitting the starlight with model populations. If a short, intense burst dominates the light, the mass can be overestimated unless you allow for bursty histories. Star formation rates combine line strengths with corrections for dust. Size estimates use careful point spread modeling to tease a half-light radius from what looks like a speck. Uncertainties are kept visible, reported as ranges, not single heroic numbers, so later work can update them cleanly. Now translate the field into a reionization map. For each confirmed galaxy, teams note whether Lyman-α is present and how strong it is. They aggregate results in narrow distance slices, estimating what fraction of sightlines are clear. Where the pass rate is high, bubbles have likely merged. Where it is low, fog hangs on. Pairing these slices with any nearby quasars and with radio limits on the 21-centimeter fog stiffens the timeline. An uneven sunrise. Bright plateaus beside darker valleys moving toward daylight. Dust turns the mid-infrared images into texture. Warm emission traces tiny grains and organic-like molecules that glow when starlight excites them. Comparing that glow to the near-infrared starlight tells how quickly recycling is underway. Early fields show more dust than many models predicted at these ages, implying that the first stellar generations lived and died on tight schedules. That extra cooling power likely helped gas collapse into new stars, speeding the cycle while hiding part of the light we count. Lensing can elevate a field from good to exquisite. A small foreground galaxy or a full cluster acts like a bent window, magnifying a background source by factors of a few to tens. With careful lens models, astronomers reconstruct the unlensed size and brightness, and, in the best cases, resolve clumps within a galaxy otherwise too tiny to separate. Time delays between multiple lensed images occasionally turn the field into a clock, adding independent distance checks and tightening the mass map of the lens. Every deep field invites false alarms. A dusty, nearer galaxy can mimic the colors of a very distant one. A detector quirk can plant a speck that looks real. A cool dwarf star can slip through cuts. This is why public releases matter. Other teams reprocess the same frames, test different noise models, and point other telescopes at the best claims. The result is a pruned, sturdy roster of early galaxies that multiple methods agree on. What precisely did this particular field add? 3 strong points. First, the number of compact, active systems at great distance is solidly above early expectations, even after conservative trimming. Second, dust signatures appear in a meaningful fraction of confirmed sources, pushing chemical recycling early. Third, line ratios in many spectra favor young, metal-poor stars as the main drivers of clearing rather than dominant black hole activity, though subtle signs of small central engines are present in a subset. The lesson flows outward. A single careful field does not rewrite the book, but it calibrates the chapter headings. It tells modelers how to tune star formation recipes, feedback strength, and the early mix of stellar masses. It tells planners where to spend the next hours of telescope time. On fainter bins to test completeness, on lens-rich patches to resolve internal structure, and on coordinated X-ray and radio follow-ups to catch hidden engines and raw fuel. Bring the scale back to something you can hold. Think of one confirmed source as a postcard. On it is a thin rainbow with a neat step at one edge, a few bright spikes at known places, and a smooth slope between. That page carries a date from the first few 100 million years. Stack enough postcards and you get a calendar you can trust, written not in equations but in light. The quiet headline from this field is simple. The early universe assembled quickly along the dark matter web, forming compact, efficient galaxies, while dust and feedback joined the story sooner than expected. The rules held, the tempo quickened. With each careful spectrum, the fog of our ignorance thins a little more, and the picture gains both contrast and calm. Shift to the worlds that orbit other suns, because Webb's quiet precision is reshaping that story too. Most targets so far are hot giants, large, puffy planets that pass in front of their stars and cast deep, clean signals. These are the training grounds. Before a transit, the star's spectrum is recorded as a baseline. During the transit, a thin ring of starlight filters through the planet's air. Afterward, the baseline returns. Subtract the before and after from the during, and what remains is the planet's atmospheric fingerprint, tiny notches where molecules soaked up specific colors. Water vapor draws smooth troughs. Carbon dioxide carves a sharp feature. Methane leaves a ladder of marks. Clouds and hazes flatten the pattern, telling us how misty the sky is. To move from hot giants to smaller, cooler worlds, teams apply 3 habits. First, repetition. A single transit is a hint. Several stacked together become a measurement. Second, target choice. Small, dim stars, cool red dwarfs make planets look proportionally larger, so the depth of the transit is easier to see. Third, cleanliness. Instrument drifts and star spots mimic signals unless carefully modeled. Webb's detectors are stable, but the discipline remains the same. Publish the steps that turned raw counts into a clean spectrum so others can check the work. Interpreting these spectra is a calm balance between physics and caution. A molecule's fingerprints are known from lab measurements, but the depth of each notch depends on temperature, pressure, clouds, and how high the atmosphere puffs above the planet. Retrieval codes explore many combinations and return families of answers that fit the data. Honest reports show the range, not just a single best number. That is how a field avoids convincing itself too soon. Heat maps add another dimension. When a planet slips behind its star, the total light drops by the planet's dayside glow. Measuring that difference across colors sketches a rough temperature map. Some hot Jupiters move heat well, spreading it from day to night. Others trap it, leaving a huge contrast. Those patterns speak to winds, chemistry, and cloud formation. Again, these are not Earth analogs. They are wind tunnels where methods mature. What about smaller planets, the ones that tug at human hopes? The realistic short-term path is sub-Neptunes and super-Earths around quiet, nearby red dwarfs. Their atmospheres, if present, may be rich in hydrogen or heavier gases like water and carbon dioxide. Hydrogen-rich skies are easier to read because they are puffier. Heavier atmospheres sit lower and hide their signals more. Clouds can erase features entirely. Even a non-detection helps. A flat spectrum can rule out a deep hydrogen envelope and point toward a denser, more compact sky. Biosignatures enter the conversation here. And language matters. A biosignature is not a single molecule. Oxygen alone can appear without life in certain exotic scenarios. Methane alone can be volcanic. The strength comes from combinations that are hard to maintain without biology, plus context from the planet's temperature, the star's activity, and the system's history. Webb will help by reading key molecules with care, but ruling out non-biological sources often needs a chorus of observatories and years of patient cross-checks. The right promise is modest and solid. We are building the tools to recognize interesting cases, not declaring life at first glance. Free-floating worlds are a quieter thread. Some planets have no star, either born alone or flung away by gravitational tugs. They glow faintly in infrared while they are young and warm. Webb can catch that glow in rich star-forming regions or see their silhouette if they drift across dense background star fields. They will not be common prizes, but each one expands the census of what a planet can be. Rogue signals from brown dwarfs, objects heavier than planets but too light to sustain star-like fusion, also teach lessons. Their skies form clouds of silicates and metals at temperatures far above any earthly storm. Watching those clouds shift in and out of view as the object rotates gives a laboratory for atmospheric physics under exotic conditions, sharpening the same retrieval tools used for planets. There is a practical loop between galaxy work and planet work. The early efficiency of star formation that Webb sees implies that the ingredients for rocky worlds, carbon, oxygen, silicon, iron, were set into circulation earlier than expected. That does not prove early life, but it nudges the window for when habitable materials existed. Meanwhile, precise planet spectra drive instrument teams to squeeze even steadier baselines from Webb, improvements that echo back into the faintest galaxy measurements. 2 pursuits, 1 craft. Guardrails keep hopes sober. Star activity can fake features. Flares and spots change the star's spectrum in ways that might be mistaken for a planet's air. Observers counter by monitoring the star over time and using reference stars in the same field to remove shared noise. Instrument persistence, the detector's memory of bright signals, can linger and imprint a false dip. Pipelines flag and correct it. Systematics are not failures, they are chores that must be done before a claim is earned. Looking a little forward without hype, the near-term wins will be cleaner water and carbon dioxide measurements on a short list of small, cool planets. First, sturdy limits, or tentative detections, of methane in those same skies, and early evidence for clouds or hazes that set the stage for future attempts at oxygen and ozone. Each success will arrive quietly, as a better fit curve, a narrower range, or an agreement between 2 teams using different methods. That is the sound of science settling, not shouting. One more step ties the human scale to the cosmic. The molecules Webb reads, water, carbon dioxide, methane, are simple. Their fingerprints are gentle, notches riding on faint, stretched light. Yet those notches let us say sentences no one could say a generation ago. This faraway world has water vapor in its sky. That one's day side is hotter than lava, another hides its chemistry under high clouds. In time, on a handful of small, quiet systems, we may be able to say, this atmosphere is compact and likely heavy. This one is light and escaping. This one shows an odd mix that deserves more time. If a single line must carry this section, keep it plain. Webb is turning exoplanet atmospheres from speculation into measurement. One calm spectrum at a time. Hot giants train the method. Smaller worlds are next. Biosignatures are not trophies to grab but puzzles to solve with combinations, context, and patience. The same care that dated the universe's first city lights will, slowly, make distant skies readable. We will close the narrative soon with a steady recap. What shocking really meant, how the pieces fit without breaking physics, and where gentle curiosity should look next. Before that, one last stop in the early universe dust chemistry, and the first grains that set the pace for cooling and starbirth, because tiny solids turn darkness into structure faster than expected. Start small, dust small. In the early universe, before planets, before long-lived stars, the first solids were tiny grains, specks of carbon, silicates, and metal compounds, no bigger than smoke particles. They formed in the cooling breath of dying stars and in the debris of supernovae. When those explosions faded, the ash did not vanish. It drifted, clumped, and began to change how gas behaved. Dust seems like a footnote, but it is a switch. With dust, clouds shed heat faster, collapse more easily, and shield fragile molecules from harsh radiation. In plain terms, tiny grains help turn darkness into structure. Where did the first grains come from so quickly? The earliest contributors were massive, short-lived stars. They burn bright, die young, and leave supernova remnants filled with dense, cooling knots, good places for solids to condense. In slightly later times, bloated red giants also exhale material that crystallizes into grains in their winds. Webb finds evidence for both paths. In the mid-infrared, MIRI sees warm, gentle glows from small grains and from carbon-rich molecules whose ring-like shapes respond to starlight. Their presence this early means the universe recycled matter on tight schedules. Make stars, let them explode, harvest solids, repeat. Dust is more than a coolant. It is a canvas for chemistry. Atoms and simple molecules stick to grain surfaces and meet there, forming more complex species than they could in thin gas. Water can form this way. So can simple organics. When a star later warms the region, those ices and compounds evaporate back into the gas, seeding newborn systems with richer ingredients. Webb's spectra pick up hints of these processes. Broad features that match tiny carbon rings, smoothly rising continua from warm silicates, and in some places, signatures that look like simple ices. The grains also change what we see, and that matters for early galaxy math. A little dust can hide a lot of blue light. If you count starlight without correcting for dust, a young, compact galaxy can look older or heavier than it is. Webb helps twice over. First, near-infrared colors tell you when dust is pushing the spectrum redward. Second, mid-infrared glow measures the dust directly. Combine the two and you trade guesswork for bookkeeping. You learn how much light was hidden and how much star formation you missed behind the veil. There is a gentle feedback loop here. Dust cools gas, making starbirth easier. Starbirth creates massive stars. Massive stars live fast and die, creating more dust. That cycle can run quickly in small, dense galaxies. It explains why some early systems look both bright and veiled, like a forge glowing through smoke. It also explains why reionization, the clearing of the cosmic fog, was patchy. In busy neighborhoods, intense star formation produced both the ionizing light that carves bubbles and the dust that scatters certain signals, making some windows look cloudy even as the fog thinned. Grain size and makeup matter too. Very small grains heat up and cool down quickly, flickering in response to starlight. Larger grains stay warm more steadily and emit a smoother glow. Carbon-rich grains and silicate-rich grains leave different fingerprints. By fitting these shapes, teams infer not just dust present, but what kind, how warm, how big. Early fields show mixtures that suggest quick production and early processing grains formed in supernova ejecta, then reshaped in shocks and by UV light until only the sturdy types remain. You may hear about PA features, a shorthand for polycyclic aromatic hydrocarbons, those small ring-like carbon molecules. They are common in modern star-forming regions and tend to trace places where young stars bathe dust in moderate radiation. Seeing PAH-like features at high distance tells us that carbon chemistry was already busy. But caution applies. Harsh environments can destroy these molecules, and metal-poor galaxies may make fewer of them. Webb's detections so far show variety, some early systems rich in these features, others nearly bare. The lesson is not one recipe but many, depending on local conditions. Dust also helps reveal hidden engines. A feeding black hole heats nearby grains, making a compact, warm mid-infrared glow. If the near-infrared spectrum shows starburst lines, but the mid-infrared screams hot dust in a tight core, you likely have both. Stars building in rings or clumps, and a small central engine adding its own heat. Separating the two prevents double counting and clarifies who is doing what in shaping the neighborhood. There is a practical side for planet stories. The same grains that cool star-forming clouds also populate protoplanetary disks, the flat, dusty pancakes around young stars where planets grow. Grains collide, stick, and snowball into pebbles, then rocks, then worlds. If dust appeared early and often, then the raw materials for rocky planets were in circulation sooner than many models assumed. That does not guarantee early habitable planets, but it narrows the gap between first stars and first solid surfaces. How sure are we about the dust rush? The case rests on converging clues. Mid-infrared brightness that matches warm, small grains. Spectral shapes that line up with carbon rings and silicate bands. Near-infrared colors that demand dust to explain their slopes. And, in a few joules, resolved structures, dark lanes, and glowing rims that look exactly like dust, doing its two jobs: hiding light and helping gas cool. Add in the fact that early galaxies show signs of quick stellar recycling, and the timeline holds together. As always, guardrails stand. Some mid-infrared features can be confused by foreground contaminants or instrument artifacts. Teams answer by reprocessing with different pipelines and checking the same target with multiple instrument modes. Photometric redshifts can misplace a dusty nearer galaxy into the very early bin. Spectroscopy fixes that. And starburst light can masquerade as hot dust near a black hole. Multi-wavelength crosschecks infrared, X-ray, radio sort the balance. Bring the scale back to something familiar. Imagine a handful of soot drifting through a cold room. That soot absorbs warmth and radiates it away, cooling the air. It also gives steam a place to condense. The early universe worked like that room. Tiny grains took heat out of gas clouds, shadowed delicate chemistry from harsh light, and offered surfaces where bigger molecules could form. The result was not magic. It was acceleration. If one sentence can carry this section, let it be simple. Dust arrived early, worked fast, and quietly sped up the universe's move from smooth gas to structured light. With Webb's cold eyes, we are not guessing. We are measuring the glow of the grains themselves and watching their fingerprints rise from the noise. Next, we will close the loop with a calm recap, what shocking really meant, why none of this breaks physics, and how the pieces fit into a faster, clearer timeline from first stars to first worlds. Gentle pace, plain words, steady wonder. Let's gather the threads into a clear timeline and keep the language plain. First came gravity laying tracks in dark matter. Along those tracks, gas pooled. The first stars switched on in tight neighborhoods, pouring high-energy light into surrounding hydrogen and carving clear pockets. Within a few tens of millions of years, those pockets overlapped. Reionization advanced like an uneven sunrise. In the same places, small, concentrated galaxies began to flare in bursts, blue, bright, and compact, using their gas quickly, pausing as winds and supernovae pushed back, then lighting again when the gas cooled. Webb's deep fields catch these systems not as rumors but as measured places, distances fixed. Chemistry read, dust seen. Place black holes on this calendar. Seeds formed early either from the deaths of massive first-generation stars or from rare direct collapses of pristine gas clouds. In a few neighborhoods, those seeds fed well and grew fast. Their cores glowed as modest active nuclei, and in rarer cases, as young quasars. Their heat and outflows nudged the timing of star formation nearby, clearing centers or compressing edges into rings. None of this required new physics. It required early opportunity and good access to fuel. Now put chemistry on the same axis. The first stars forged heavier elements and scattered them in explosions. Tiny grains of carbon and rock condensed in the rubble and in the winds of bloated stars. Those grains radiated away heat, shaded fragile molecules from harsh light, and offered surfaces where water and simple organics could form. In Webb's mid-infrared vision, that chemistry glows. The conclusion is simple. Recycling was fast. By the time the universe was a few 100 million years old, young galaxies already carried dust, not as an exception, but as a theme. How sure are we? Because the same story repeats across different kinds of evidence. From colors alone, we get candidates. From spectra, we fix distances and measure line ratios that shout young stars rather than only black hole light. From mid-infrared maps, we see dust where dust was not expected so soon. From lensing arcs, we turn dots into stretched maps that show clumps and winds. From quasars, we read how clear the nearby fog is. From lensed supernova echoes, we strengthen distance scales and mass models. Independent tools, same melody. Where did shocking fit here? In the tempo. Many models scheduled these milestones later. Webb pushed them earlier by showing compact, efficient galaxies sprinkled generously in the first few 100 million years, by hinting that some black holes mattered sooner, by catching dust in places where some templates predicted almost none. We are not tearing pages from the physics book. We are revising the calendar margins we left vague. Bring the recap down to felt scales. If you compress the universe's life into a single day, the first compact galaxies Webb confirms appear in the deep night just after midnight. Reionization clears toward 1 or 2 nm, patch by patch. The sun rises close to morning. Earth cools. Complex life blooms long after noon. Humans look up in the final breath before midnight. The photons from those early hours have been traveling the whole day to reach Webb's mirror, which we unfolded in the last blink. Their message is quiet. We started early and moved fast. What remains uncertain? 3 big items. First, the true mass scale of the earliest galaxies once dust and bursty light are fully accounted for. Second, the mix of seeds for early black holes and how often each path occurred. Third, how patchy and fast reionization was across different neighborhoods of the cosmic web. Each is being squeezed by deeper spectra, wider mosaics, and cross-checks at X-ray and radio wavelengths. The direction of travel is clear. The numbers are where the debate lives. And the planets? Hot giants have taught us to read clean barcodes in thin light. Next come cooler, smaller worlds around quiet red dwarfs, where water, carbon dioxide, and methane will be measured with increasing confidence. Biosignatures remain a careful, long-term goal, built on combinations, context, and patience, not on single-molecule headlines. If one sentence must carry the timeline, let it be this: the laws held, the schedule tightened, and Webb turned whispers into dates we can write down. Keep that sentence nearby as we step into what comes next. More hours on the deepest fields, smarter lens patrols, and a sharper focus on small, quiet stars where the first truly tempting planet spectra will emerge. Turn from what Webb has found to how we will use it. Planning the next decade is like planning a garden. Soil, tools, and seasons. The soil is the sky we already mapped: deep fields with solid catalogs, lensing clusters with tested mass models, nearby stars with predictable transits. The tools are the instruments we have and those arriving soon. The seasons are observing windows when targets are high, quiet, and worth the hours. First, deepen before you widen. Adding exposure time to the best fields does more than reveal new dots. It turns shaky photometric estimates into spectra, and spectra into physics line ratios, dust temperatures, and clean distances. Longer integrations also tame systematics. Detector memory fades into noise, flat field quirks average out, and faint features become repeatable. The rule is simple. If a claim would sway a model, give it the photons it deserves. Second, widen with purpose. Wide mosaics answer a different question. Were the compact, busy galaxies, rare peaks, or the normal state of early neighborhoods? Purposeful widening means choosing strips that cross dense and sparse regions of the cosmic web, then comparing their reionization weather, how often Lyman-α gets through, how dusty the sources are, and how common small active nuclei appear. With enough area, statistics replace anecdotes. Third, patrol the natural telescopes. Strong lens clusters are time machines with schedules. Teams can predict when delayed images of a supernova should appear and be ready to catch them. Regular patrols also net new lensed arcs whose internal knots can be mapped. Each fresh system tightens lens models that, in turn, make every background target more informative. It is a small investment for large leverage. On the planet side, build a short list and stay loyal. Pick nearby, quiet red dwarfs with small transiting worlds. Commit to many visits. Stack transits until water and carbon dioxide reach firm significance. Then look for methane with the same discipline. Publish the full detrending recipe so others can reproduce the curve. If the spectrum is flat, say so. A clean non-detection is as valuable as a headline when you are building a catalog you can trust. Next, braid wavelengths. Pair Webb's infrared with precise optical spectra from large ground telescopes to refine stellar ages and metallicities in early galaxies. Add X-ray checks for faint accreting black holes. Add radio maps of cold hydrogen and emerging 21-centimeter structure to see where the fog still sits. Multi-wavelength data turn each target from a single clue into a small case file. They also catch mismatches that signal new physics or unmodeled systematics. Keep human time in view. Data archives and open pipelines let students on modest laptops repeat flagship results. That culture matters. Surprise becomes understanding only when many eyes try to break a claim and fail. Plan for that. Release raw and clean frames, document every correction, and invite replication. The pace will feel slower than a feed full of record-breaking headlines, but the foundation will be thicker. A word about theory. The most useful models will not simply match Webb's plots. They will predict relationships that new data can test. For example, tie star formation burstiness to halo mass and environment, and forecast a specific trend in line ratios with clustering strength. Or link black hole seed channels to the shapes of dusty cores and predict how often small nuclei should appear at a given epoch. Then let the sky answer. Theory earns its keep when it sticks its neck out. Technology will help too. Better noise models for detectors, improved micro-shutter calibrations, and smarter scheduling to dodge thermal drifts can squeeze more precision from Webb without changing hardware. On the ground, adaptive optics and new spectrographs will turn faint red targets into usable, high-resolution spectra, feeding back into how we interpret Webb's lower resolution but deeper views. Finally, keep the story clean for the public. The truth is already dramatic, a universe that built early and fast but stayed inside its rules. Say that plainly. Avoid phrases that bend meaning for clicks. A patient audience will meet you where you are if the path is clear. This channel's promise is calm wonder backed by careful sources. That trust is an asset. Grow it by being precise when it matters and gentle everywhere else. If this plan has a motto, it is humble boldness. Aim deeper, share more, test harder, accept revision. The reward is a map of beginnings that will still look good 10 years from now because it was built slowly, checked widely, and told honestly. Questions you might quietly ask while drifting off deserve plain answers. Did Webb break the Big Bang? No. Webb looks at the light that left young galaxies long after the Big Bang. It shows that structure formed earlier and faster than some models predicted. But the expansion of space, the cooling of the early plasma, and the formation of hydrogen all stand. The timeline is adjusted, not erased. Are these impossible black holes real? The phrase is drama. What is real are early, surprisingly massive black holes. They likely began as large seeds from giant stars or rare direct collapses, and then fed efficiently. Webb weighs their influence through broad emission lines, hot dust near the core, and subtle high ionization features. The results say, early and hungry, not older than time. How can we trust faint, stretched light? Because different methods agree. Photometric colors flag candidates. Spectroscopy locks distances. Lensing turns dots into maps. Quasars and the 21-centimeter radio search track the fog. X-rays and radio check for hidden black holes. When independent tools point to the same conclusion, confidence rises. Where they do not, the field slows down and tests again. What does dust so early imply? It implies quick recycling. Short-lived stars lived, died, and seeded their surroundings on tight schedules. Dust cooled gas and shadowed molecules, speeding star formation while hiding part of the light. Webb sees the glow of those grains directly. That is not guesswork, it is measurement. Will Webb find life? Webb can read key molecules in some small, cool planets around quiet stars. It can report water vapor, carbon dioxide, methane, and perhaps detect hints of clouds and temperature patterns. A secure biosignature will require combinations that are hard to explain without biology plus careful context about the star and planet. That likely needs years, multiple observatories, and boringly careful work. The right promise is that we will know which targets deserve that attention. Why do headlines keep changing masses and distances? Because early estimates use limited data and simple assumptions. As deeper spectra arrive, dust corrections improve, and bursty star histories are allowed. Some masses shrink, and some distances tighten. That is progress. The aim is not to be first, it is to be right in the end. Could we be fooled by lensing? Lensing can boost and stretch a background galaxy, making it look brighter and larger than it is. That is why lens fields are modeled in detail using multiple images, and when possible, time delay measurements from lensed supernovae. With good models, magnification is a tool, not a trap. Is Webb alone in this? No. Hubble built the scaffolding. Large ground telescopes supply high-resolution spectra. X-ray and radio observatories see engines and cold gas. Future missions will bring sharper tools. Webb's gift is unmatched cold sensitivity to infrared light, the color where the oldest photons now live. It is the right ear listening to the right notes. Why does all this matter to me? Because it is the origin story of structure, and you are made of structure. The oxygen in your lungs, the iron in your blood, the calcium in your bones, those came from stars. Knowing when and how the first star cities lit up places you on the timeline with less guesswork and more light. What should I remember when this video ends? 3 simple lines. The universe built early and fast along tracks, gravity laid in dark matter. The rules held, our schedule moved. And a cold gold mirror a million miles out is turning whispers from the first city lights into a story you can follow with your eyes closed. If your mind wants one last picture, a quiet field that looked empty now holds hundreds of distant homes. A thin rainbow with a single neat step turns a smudge into a date. A tiny dip in starlight reveals water vapor on a world you will never visit. All of it honest, all of it measured, all of it pointing to the same steady truth. The cosmos did not wait to get started. It got busy early, and we finally have the ears to hear it. Let's close with a gentle, complete arc. No rush, no jargon, just the path we walked. We began with a hook, Ancient light arriving at Webb's mirror with messages from the first few 100 million years. We outlined the tools NIRCM's maps, NIRS specs barcodes, MIRI's warm glow, and the habits that turn hints into anchors. Longer exposures, careful cleaning, spectra over headlines, and open data that invites replication. Then we followed the evidence into a simple theme. The early universe assembled quickly along dark matter tracks, forming compact, efficient galaxies, with dust and feedback joining the story sooner than expected. Black holes were not older than time. They were early enough to matter. Reionization was not a switch. It was a patchwork dawn. We layered in beacons. Quasars acted as lighthouses, tracing how far the fog had cleared. Lensed supernovae echoed through curved space and tightened our distance rulers. Lensing arcs turned dots into maps, revealing clumps, winds, and rings in tiny disks. Across fields, the pass rate for Lyman-α sketched an uneven sunrise. Some neighborhoods clear, others still misty, all drifting toward daylight. None of this broke physics. It compressed the schedule and sharpened the calendar. We tied in chemistry and grains. Pa-like features and warm silicates showed that tiny solids were already doing their quiet work, cooling gas, shielding fragile molecules, and hiding part of the light we count. That early recycling meant the raw materials for rocky worlds were circulating sooner than expected. On the smallest scales, Webb read thin barcodes in exoplanet skies, water vapor, carbon dioxide, clouds and heat patterns on hot giants. Practice runs for smaller, cooler worlds that will test our patience and our methods in the best way. We kept guardrails up. Photometric guesses yielded to spectroscopic checks. Lensing models absorbed time delays and multiple images. Dust corrections came from measurements, not wishes. Claims were trimmed when deeper data arrived, and that trimming was treated as growth, not loss. Across wavelengths, different observatories covered one another's blind spots. Ensemble seeing replaced single image certainty. We also looked forward with humble boldness. Deepen the best fields, widen with purpose, patrol lensing clusters, pick a short list of small, quiet stars and return again and again. Share code and frames. Let theory make testable bets. The next winds will be quiet but sturdy. Cleaner planet spectra on sub-Neptunes and super-Earths. Firmer mass estimates for the earliest galaxies. Sharper maps of reionization's patchwork. And more beacons that turn stretching space into rulers. If there is a feeling to carry away, let it be calm wonder. A gold honeycomb sitting in cold shadow is catching light that left when the universe was a child. That light says, we started fast. We grew within the rules. We left clues everywhere, tiny but honest. Your part is simple, listen. Let the story run like a low tide in your mind. When you wake, it will still be there, steady and clear. One last soft call to action, appropriate to the night. If you want more slow, science-true journeys like this, tap like and subscribe so the algorithm knows to bring you back. No rush, no noise, just a steady thread of the cosmos told plainly. Thank you for sharing this quiet exploration. May your sleep be deep and your curiosity bright when you open your eyes again. The sky will be waiting, and Webb will still be listening from its cold, patient orbit, turning whispers into dates, and dates into understanding we can carry gently through our days. Epilogue. Hold the sky a little closer. We spent hours walking through quiet evidence. Deep fields, lensed arcs, damping wings, warm dust, and thin spectral barcodes, until a simple picture settled in. A lawful universe that started quickly. Before we part, let's seal that picture with a final, human-scale pass you can replay whenever you need calm. First, the headline in plain words. Webb did not overturn physics, it sharpened time. The earliest star cities were compact and efficient, lighting up faster than many models scheduled. Dust arrived early, cooling gas and hiding some of the light we first tried to count. Small black holes learned to feed and, in some places, mattered sooner than expected. Reionization progressed patch by patch like an uneven dawn, driven mostly by star formation with local help from young nuclei. All of this rests on measurement, not wish. Second, a 1-minute memory exercise. Picture 3 cards. Card A shows a thin rainbow with a neat step at the blue edge and a spike or two at known places. That is a galaxy's spectrum distance fixed, mood readable. Card B shows a graceful, stretched arc. That is the same kind of galaxy seen through the glass of a foreground cluster, clumps resolved, winds mapped. Card C shows a shallow dip in a steady star's light, and beneath it, Soft notches that match water or carbon dioxide. That is a planet's sky, read by subtraction. If you can recall those 3 cards, you can reconstruct the whole story whenever you like. Third, what changes next, not for drama, but for depth? Fields we already trust will get longer exposures. Mosaics will widen to test how typical the busy early neighborhoods were. Lensing patrols will catch more echoed supernovae. A short list of small, quiet stars will anchor the first sturdy spectra on cooler, smaller worlds. The rhythm will feel slow from video to video, but the curve bends toward clarity. Fourth, a gentle responsibility. Words matter. We choose phrases that travel well without bending truth. Faster assembly, early dust, compact starbursts, patchy reionization, efficient feeding. If a number shrinks after deeper data, we say so. If a claim stalls at candidate, we wait. The sky is generous. We do not need to decorate it. Finally, bring it all the way home. Somewhere above you, a honeycomb of gold sits in cold shadow, listening. Tonight it may be staring at a field that once looked empty, letting ancient photons stack into something you can understand with your eyes closed. That is the real gift. A path from faint, honest signals to sentences we can say softly in the dark. If this journey eased your mind or woke your curiosity, let it drift with you into sleep and meet you again in the morning. The cosmos keeps steady time whether we watch or not. When you return, it will be waiting busy, lawful, and, thanks to Webb, a little less mysterious. Good night and clear skies, wherever you are.